Welcome to this video on the physics of carbonation. I want to discuss primarily how you make a beverage carbonated and how it goes flat. In other words, how CO2 goes into solution and how and why CO2 comes out of solution. You're all familiar with blowing up a balloon. When you blow up a balloon, what causes it to expand? Is it being filled with something? Well, yes, of course it is. It's being filled with air. Let me show you what I mean. Here's my balloon in the middle of the screen, and I'm going to add some molecules to it by pressing this Add button on the left. The balloon expands a bit, not because I put something in it per se, but what I put in it is composed of particles that are moving very rapidly, and the collective collisions with those particles in the wall of the balloon are what keeps it expanded or extended. The more molecules I add, the bigger the balloon gets. If I take molecules away, the balloon gets smaller. So in this way of looking at things, pressure is simply a manifestation of the collective impact of all of the particles or molecules inside the balloon. Temperature also has a molecular explanation. Temperature is just simply a measure of the energy or the speed of the molecules. If I heat things up, the molecules move faster, and the molecules hit the side of the balloon with more vigor, and the balloon expands. Cool things down, the molecules move slower, and the impacts are smaller, and the balloon decreases in size. So that's the kinetic theory of gases in a nutshell. Pressure is due to the collective force of trillions and trillions of collisions per second, and temperature is a measure of molecular speed. Next, I want to talk about the concept of equilibrium, and I want to do so by talking about a cocktail party. Imagine a large hotel ballroom with a left side and a right side, divided down the middle with a wall. There's a door in the center of it. Let's say I put some people over here on the left side of the ballroom. 20 people, say. They're milling about. Let's say they're milling about more or less randomly. What happens if I now open the door that separates the two rooms? By their random walks, some will eventually make their way from the left side to the right side, and some will make their way from the right side to the left side. And after a period of time, these two numbers of people on the left and the people on the right will more or less equilibrate. That's what I mean by equilibrium. It's not that nothing's going on, it's that there's an equal number of things going on in one direction versus another. At equilibrium, just about as many people are going from left to right as right to left. Of course, as you may have already ascertained, I'm really not here to talk about cocktail parties. Really what I'm representing here are gases. These red dots are gas molecules. And I'd like to ask the question now, if I wanted to keep, on average, 20 gas molecules on the left when I open the door, what could I do over here? Well, one thing I could do is add 20 red molecules over here, and now the system is already at equilibrium, so that when I open the door, the number of red on the left should stay about 20, and the number of red on the right should stay about 20. Let's see if that's true. And there's a little variation around the number 20, but that's basically true. They both stay at about this 50-50 split. Now let me ask a slightly different question. If I have my 20 molecules on the left, is it possible that I could keep them in equilibrium, that is, continue to have about 20 molecules on the left, if I add 20 molecules of a different type, blue molecules, on the right? Now what happens when I open the door? Well, watch the numbers. Start out with 20 red on the left and 20 blue on the right, and we open the door. Note that the number of blue molecules is going up on the left and the number of red molecules is falling on the left. So the blue molecules, the existence of the blue molecules on the right didn't help keep the red molecules on the left. Why is that? It really has to do with how tiny molecules are. If the molecules in air were about the size of a tennis ball, their nearest neighbors would be like a mile away. So gas molecules don't interact with each other very often or very much. So the fact that there were blue molecules on the right when we started this demo is of really no consequence to keeping the red molecules on the left. They just simply don't interact very much. We can actually quantify this with a little experiment. I'm going to set a timer and add my 20 molecules on the on the left. And I'm going to watch this timer to see how long it takes to get to a 10-10 split in these 20 molecules. 10 on the left, 10 on the right. Open the door, the timer starts to go. Molecules randomly make their way from the left to the right. It got close to a 10-10 split, but this is random, keep in mind, so sometimes it will go up and sometimes it will go down. And there we are, 19 seconds. Now let's do the same thing. Our 20 molecules on the left and 20 blue molecules on the right. And my hypothesis is that the existence of the blue molecules will not impede the left's molecules' march toward equilibrium because they are dissimilar molecules and they don't interact. Set the timer and let's open the door. Remember, we had 19 seconds before, and we're looking for something near 19 seconds this time, if my hypothesis is correct. Keep in mind, this is a totally random process, so sometimes it could be 12 seconds, sometimes it could be 25 seconds. I'm not expecting to see exactly 19, but I hope to at least quantitatively make the point. And there we go, 17 seconds. So I think that's at least helps you understand that it's plausible that the existence of molecules of a different type, in this case blue, could not keep the red molecules in equilibrium on the left. Now, finally, let's talk about carbonated beverage, which is the real subject of this presentation. And I want to talk about how gas gets into and out of solution. Well, this two-chamber demo that I've been showing you is really just sort of a metaphor for a liquid gas system, like champagne in a bottle. Let me just sort of turn this on end. So here I have just a very simple model of some type of container that contains a beverage with liquid on the bottom and some type of headspace on the top, and some way of sealing the top of the bottle. I can have it open or I can have it closed. In this model, the liquid gas surface here across the middle of the container is like the wall between the two chambers in the previous demo, in the two-chamber demo. So now I want to do the same type of thing that I did in the previous demonstration. I'm going to add some molecules to one side of this container down in the liquid, in this case 40. And now I'm going to let the simulation run forward. Some of the molecules will make it through the surface and some of them won't, just as some made it through the door. And in very short order, you see that this system comes to equilibrium. The CO2 molecules that were in solution, some come out, and some CO2 molecules that are in the headspace go back in. And over time, we reach some type of equilibrium. In this case, it looks like about 30-ish in the headspace and 10-ish in the liquid. And if I open the top of the container, I destroy that equilibrium. Now I have fewer gas molecules in the headspace, and my beverage has gone flat. So that's how CO2 gets out of solution, one molecule at a time. That's a process called diffusion. Now let's see how we get CO2 molecules into solution. I'm going to add some molecules into the headspace, and by random chance, sometimes some will go into solution, and over time we start to reach an equilibrium. The more molecules I put in the headspace, the more CO2 molecules I get into the liquid. So the lesson here is that if you want to carbonate your beverage, you need to have a closed container and put lots of CO2 molecules in the headspace, i.e. you have to put a highly pressurized CO2 gas in the headspace. Then through random movement of the molecules, sometimes they'll be going slow enough upon impact that the water will be able to essentially reach out and grab them, and that will then become an aqueous molecule of CO2, and with enough CO2 molecules in solution, we'll have a carbonated beverage. This can easily be done with the Perlini cocktail carbonating system, for example. Now I'd like to ask another question similar to what I asked before with the two-chamber demo. What if I add, say, 30 molecules of CO2 in the liquid of this container and ask what I would have to do to the headspace to keep those CO2 molecules in equilibrium? Well, just as with the two-chamber demo, I could add 30 molecules to the headspace, and therefore I would expect that I might have as many leaving solution as entering solution, so I would keep a healthy percentage of those CO2 molecules in solution. Let's see if that's true. It takes a while for the animation to begin. And sure enough, that is borne out. I've got something like 30 molecules in the headspace and 30 molecules in the solution. Now, as before, let's ask again a similar question. What if I put, say, 30 molecules of CO2 in the liquid, but 30 molecules of something else, perhaps nitrogen, in the headspace? Now would I expect to be able to maintain the same concentration of CO2 in solution? If when I start this animation, will I see this number stay at 30 or will it drop? My hypothesis, as before, just as before, is that these blue molecules, these nitrogen molecules, won't keep the CO2 molecules in solution. And again, we have to wait for the simulation to begin. And as you can see now, the number of red molecules, the CO2 molecules, is dropping precipitously, and the number of blue molecules is growing, in fact, in the liquid. So just as before, the existence of the nitrogen molecules, the blue molecules in the headspace, had no effect on keeping the red molecules in solution. This is in fact an expression of something called Dalton's law. I can't keep molecule A in solution in the liquid with a different molecule B in the headspace. If I want to keep molecule A in solution in the liquid, I need to have a high concentration of molecule A in the headspace. This is essentially the principle behind the Perlage-Champagne preservation system. There's a couple other important points I want to talk about here. First, with one that's unique to CO2. CO2 has a unique property that when it dissolves in liquid, rather than just swimming around as individual CO2 molecules in solution, or aqueous CO2 molecules, CO2 also combines with water, which is what most beverages are composed of. CO2 combines with water to make carbonic acid, or H2CO3. I can demonstrate that here. These little compound shapes here with a red and a black stuck together, That's meant to represent a CO2 molecule attaching to a water molecule and forming H2CO3, or carbonic acid. Now this carbonic acid is important because it does two things. It gives CO2 a completely separate mechanism for becoming absorbed by the liquid. So you can see that there are some molecules running around as just individual CO2 molecules, but there's also these compounds of CO2 stuck to a water, or H2CO3. So there's more ways for CO2 to exist in solution than there are other gases. For example, if I do this with nitrogen, there's only one way for nitrogen to be in solution, and that's as individual nitrogen molecules. So therefore we don't get quite as much nitrogen in solution as we do with CO2, because CO2 has different modes of being in solution. So this makes CO2 more soluble in liquid than just about any other common gas. Carbonic acid also gives carbonated beverages a distinct tartness, because carbonic acid is a neutral flavored acid that doesn't really yield any flavor other than tartness. That's why a beverage like Coca-Cola tastes so horrible when it's flat, because it's a very sugary beverage, and that tartness helps balance the sweetness. But when it goes flat, you're just left with the syrupy sugariness behind. One last very important point to make about the solubility of gases and liquids is it turns out the solubility of gases in a liquid is extremely temperature dependent. The colder the liquid is, the more gas can fit in solution. This is the opposite of solids, where it's easier to dissolve a solid in a hot liquid. You've all seen this, trying to stir in a teaspoon of sugar into iced tea versus hot tea. But with liquids, it's the reverse. The slower the molecules are going in the headspace, the easier they are to be grabbed by the intermolecular forces of the water. Let's see if this is true. Add some molecules to the headspace, and most of these are just going too fast to go into solution. But let me turn down the temperature now. And now the intermolecular forces between the gas molecules and the liquid are able to grab the molecules and pull them into solution if they're moving slow enough. So you can see the huge difference as I turn down the temperature. Now these molecules are able to dive into the water, as it were, and become aqueous molecules of solution. Contrary-wise, if I put the temperature back up, these molecules are now forced out of solution and into the headspace. And now look, most of the molecules are in the headspace. Turn the temperature down, and the molecules then go back into solution, and it changes the equilibrium balance between the percentage of molecules in solution versus the percentage in the headspace. With CO2, this temperature dependence is dramatic. The difference between the amount of CO2 that can dissolve in solution at room temperature, around say 72 degrees Fahrenheit, versus refrigerator temperatures around 5 or 10 degrees, or I'm sorry, 30, say about 40 degrees Fahrenheit, is a factor of 2.5. So in other words, 2.5 times as much CO2 can dissolve into cold water as room temperature water. And that's why carbonated beverages need to be cold. If you let them warm up with the top off the bottle or the can, they quickly go flat. So now we've seen how molecules get into and out of solution. It's one at a time. One molecule at a time going in, one molecule at a time coming out. This is a process called molecular diffusion. In my demos here, there's only 20 or 30 molecules. If this were, say, a bottle of champagne, there would be trillions of molecules. But there's another way that bubbles come out of a carbonated beverage that I'm sure you're familiar with. What other thing do you notice when you have a carbonated beverage that you've poured into a glass? That's right, bubbles. Here's a little model of a champagne flute with some champagne in it, or some other carbonated beverage. And there is one thing that's important to know about what happens when you put a liquid in a glass. You can never completely wet the sides of the glass. There are imperfections and debris or particulates that might be stuck to the side of the glass, and those imperfections in the wall of the glass make it impossible for the liquid to completely get everywhere as you're filling the glass. So here's as I fill this glass to the brim with liquid, because of the scratch in the bottom of the glass, there was one little tiny microscopic bubble of air that didn't get completely wetted by the liquid. This is completely inevitable. What the force that keeps this little bubble in place is something called surface tension. There's a skin over this bubble that's formed by the liquid-gas interface, much like the membrane of a balloon. And at these attachment points right here, that force is provided by something called surface tension, the same force that allows water bugs to skitter across the top of a pond. And that force is actually remarkably strong. So it holds that bubble there, even with all the agitation of a liquid filling the glass. Now, as I mentioned, this surface too is a liquid-gas interface. So if I were to add molecules of gas, let's say CO2, to this system, randomly, sometimes molecules are going to cross that liquid-gas interface and inflate the bubble to such a size that it is now so buoyant that it breaks away from the surface tension that was holding it down here. And now it begins to rise to the surface. And as it rises, it will continue to gather CO2 molecules from this liquid-gas interface by the process of diffusion, just as before. Let's keep the simulation running. And as you can see, the bubble will continue to rise and gain CO2 molecules and grow in size. But when the bubble broke away from the bottom, it left a piece of itself behind. And the process now starts all over again at this little seed bubble that it left behind. And it too grows until it's so buoyant that it breaks away because of the buoyant force overcomes the force of surface tension. And I add more molecules to the solution, and we see the same process continuing again, starting over and over and over. The bubbles always are formed from the seed bubble that's stuck in the imperfection in the glass. This is called a nucleation site. It's essentially a bubble nursery, if you will. This is why you will always see bubbles in a glass of champagne or beer coming from the same spot at the bottom or the side of the glass. That's because there is the location of a nucleation site, and it forms bubbles over and over and over again. You can't in fact have a bubble form in a carbonated beverage unless there's already another bubble at a nucleation site for it to form on. It turns out that most of the CO2 lost in these two processes is by individual molecular diffusion at the surface. Anywhere from 5 to 10 times as much CO2 is lost invisibly through the process of diffusion, one molecule at a time. These macroscopic bubbles that you can actually see, and which are so delightful to see in a glass of champagne, actually contribute very little to the loss of carbonation in the beverage. So if the surface area is the culprit, you should now be able to guess which type of glassware is best for a carbonated beverage like champagne. Would it be a wide, shallow coupe or a narrow, deep flute? Since all the loss happens at the surface area, you're much better off with a narrow, deep flute if your goal is to try to keep as much CO2 in solution for as long as possible. And there you have a very concise explanation or application of the kinetic theory of gases to the physics of carbonated beverages. It's actually much easier to understand what's going on from a microscopic perspective if you look at it at the molecular basis. And that concludes this demo of the physics of carbonation.